here we go. So the first sentence here, what is scientific notation? It is a, we're just gonna write this, it's a compact way of writing very large or very small numbers. That so we can see it. So scientific notation is a compact way of writing very large or very small numbers, and it is frequently used. So we'll do a semicolon here. Frequently used by scientists and mathematicians. That's our quick definition. So go ahead and get that written down, and we will start talking about what this looks like, how it can be written, and there's a lot of consistency to it, which is really nice. So take a couple minutes, get that written down, and we will start taking a look at some examples.
Take both of these.
Yeah. All right, so scientific notation, compact way of writing very large or very small numbers, and it's frequently used by scientists and mathematicians. Now, this first example isn't the best example for scientific notation because the number 284,000, it's a large number, but it's not that large of a number. We'll see a little bit later on where some of these numbers that are potentially really large or really, really small. The second example is a really good example. The first one's all right, but it'll at least tell us how to write these answers. So it says that the minimum distance from Earth to Mars is approximately 284,000 miles. So this is our large number example. And basically what we're looking at is every single time you write something in scientific notation, it's always multiplied by some factor of 10. And so we're going to be using exponents to describe what's going on with that. So I don't see a lot of room to write in some actual rules for this. So we're going to use some of this over to the side here. So I'm going to show you what this looks like, and then I'm going to explain how I got there. So the answer to this is 2.84 times 10 to the, let's see, 5th power. 2.84 times 10 to the 5th power. That is what scientific notation for 284,000 looks like. The main rules here are the first number has to be at least 1, but it also has to be less than 10. It has to be basically a single digit number. So single digit number multiplied by 10 to an exponent. So let's see. Single digit number times 10 to a power. All right. So I think I hear somebody maybe watching something. Let's go ahead and shut that down for now so we can get our notes taken. All right. So it's always a single digit number times 10 to a power. And so the way that we do that is we essentially just start off by looking for, good morning. We start off by looking for where the decimal is in the number. And in the number 284,000, the decimal isn't actually shown because it's the very end of the number. If it's a whole number, the decimal isn't shown. And if there was a decimal, it would be at the very end of the number. So we start over here. And we basically just move the decimal however many places we need to make that single digit number. And so if we take 284,000 and we move the decimal over, so it's here to begin with on the very end, and we move it over 1, 2, 3, 4, 5 places, we get the number 2.84, which is this number here. And because we moved it 5 places, that means we have a multiplication of 10 to the 5th power afterwards. So it's basically just the number of times you move the decimal place. Anytime you move the decimal place, you are either multiplying by 10 or dividing by 10, which is why we have this times 10 here. So 10 to the 5th power would be 100,000. And then if you multiply that by 2.84, that gives you 2.84 times 100,000, which is 284,000. And you can always double check this on your calculator, which is actually a really good idea, because you can always know if you have the right answer or not. If you're converting from a regular number to scientific notation, you can type in 2.84 and then times 10 and then to the 5th power. And when you multiply that out, it gives you the original number of 284,000. So you can always double check to make sure that you're doing this correctly. All right. So that's our large number example. Our small number example works exactly the same. It just works in the opposite direction. And the small number examples, you will always be given a decimal to begin with. Our decimal is here. And so we're going to end up moving our decimal to make a single digit number. So basically, we're going to move it all the way in between the 2 and the 6, because that would be a decimal of 2.68. So we have to move that one. 1, 2, 3, 4, 5, 6. So we moved it 6, which means we're going to get 2.68 times 10 to the, it's not the 6th power though, it's actually to the negative 6th power. And the reason is because if it was to the 6th power, we would end up with a number that's even larger than this one up here, because that would be making the number even larger. What we need to do is make this number 2.68 to get back to the original even smaller. So if you start with a decimal, you will have a negative exponent. If you start with a large number, you will have a positive exponent. And that's actually something that we should probably write over underneath example 1 and underneath example 2. So I'm going to say positive exponent here. Positive exponent, and then down with example 2, negative exponent. And if you typed in this number, 2.68 times 10 to the negative 6th power, you would get this number here, this 0.0000268. By the way, the example there says the 2004 Indonesian earthquake slowed the rotation of the Earth. Making the length of a day 0.0000268 seconds shorter. That doesn't really make sense though. If it slowed the rotation of the Earth, that would make the day longer. So I'm not really sure which one of these was wrong, but one of those is not correct. It either sped it up and made the day shorter, or it slowed it down and made the day longer. I don't know which one it was, but there was a typo here. All right. So here's our first practice. We're going to, with these first 3, change the larger numbers to scientific notation using positive exponents. And then we're going to change the smaller numbers into scientific notation using negative exponents. So positive exponents and then negative exponents. All right, so this is all about moving decimals. However far you move the decimal, that's the exponent you have with your times 10. So this first example here, 75 million. The exponent or the decimal on a whole number, again, is always at the end of the number. And so we're going to start here. And we're going to count until we can put our decimal in between two numbers to make a single digit value. So if we move our decimal 1, 2, 3, 4, 5, 6, 7 places, that'll give us 7.5, and we moved it 7 spots. So that would be 7.5 times 10 to the 7th power. Example number 3. To me, this is one of the most useless examples of using scientific notation. It's 208. But it's just teaching us how to use it at this point. It's not really talking about practicality right now. So if we start the decimal, it's after the number. We would just move it 2 spaces to the left to get 2.08 times 10 to the 2nd power, because we moved it 2 places. So what I'd like you to do is try to finish up. That was 1, 3, and 5. So try to finish up 2, 4, 5, and 6 on your own. And once you get to 2, 4, and 6, remember that your exponent will be a negative exponent because you're moving the number the opposite direction. So go ahead and work on those 4 problems. Take a couple minutes on that or less, and then we'll check back in and move the opposite direction, going from scientific notation to standard form. All right, there they are. Go ahead and take a look. See what you got on your paper. Hopefully these match up. So let's go with number 5 first. So number 5, again, we're going with the larger numbers. So this is going to be a positive exponent. So we have to move our decimal 5 spaces to the left to get in between the 9 and the 0. And that gives us 9.07 times 10 to the 5th power. When we go to the negative exponents, we're making the really small numbers a little bit larger. And so this first one, we had to move the decimal 3 spaces to the right. And so that goes in between the 8 and the 5, giving us 8.52 times 10 to the negative 3rd power, because we had to move our decimal 3 spaces. Number 4, decimal moves twice to the opposite side of the 4, so that equals 4 times 10 to the negative 2. And then number 6, we had to move it 6 times in between the 6 and the 1, so that'd be 6.1 times 10 to the -6th power. Any questions on those before we go from scientific to standard form? All right, if not, we'll go ahead and take a look at these next ones. Now, you can use a calculator for this if you want to, but you can also just do the opposite of what we did in terms of moving the decimal places to make this happen. So if you have a positive exponent, you are going to move the decimal to, just going to do this real quick, move the decimal to the right. So move the decimal to the right for those ones there. And then on the negative ones, you're going to move the decimal to the left. So these ones down here. Move the decimal to the left. So that's how we're going to either expand or make smaller the numbers that are starting in scientific notation into standard form, which is what we would consider just like how we write regular numbers. That would be standard form. So move the decimal to the right for 7, 9, and 11. Move the decimal to the left for 8, 10, and 12. So for number 7, we start at the decimal, and it says 10 times 10 to the 2nd power. So basically, you're just moving this decimal 2 spaces to the right, and then you write your answer like a regular number. So if you move the decimal from in between the 2 and the 5, and it goes after the 4, that's going to give you an answer of 254. You're just moving it to wherever it tells you to move it, or yeah, however many spaces it tells you to go. And number 9 is a little bit different because it's not just going to go after the 1. We're actually moving this 5 spaces to the right. So if we move it once, that means we still have 4 more to go. And so if we move this 4 more spaces, does anybody have any ideas what to do on that? We still have to move it 4 more spaces. Fill in with zeros, yeah. So if you move it once, there's still 4 more to go. So that means there's going to be how many zeros? 4 zeros, exactly. So it's going to be 9, 1, and then 0, 0, 0, 0, 4 zeros. And let's see, we'll go ahead and put the comma in there just so we can see this a little bit easier. That's 910,000. So basically, however far you need to move the decimal, once you get to the end of the numbers, if you still have to move the decimal more spaces, just fill in with zeros, however many more spaces you still need to move it. So it took us 1 movement to get past the 1, but we still had 4 more to go after that, so we fill in with 4 zeros. Same thing on number 11. We're moving this 3 spaces to the right, but it only takes us 2 spaces to get to the end of the number. So we have 1 more to go. So we're going to fill in with 1 0. So it'll be 1140. So that'll be 1,140. And again, you're welcome to use the calculator. You can type in 9.1 times 10 to the 5th power, and it'll give you 910,000. So that is something that you can do. Are there questions on these 3 here, 7, 9, or 11? All right, next 3, 8, 10, and 12. Move the decimal to the left. So it's the exact opposite of what we just did. And again, we're going to fill in with zeros as well. So we have to move this one 2 times, move it 2 to the left. And it's basically just moving in the direction of the positive or negative, right? If you move a decimal to the right, you're moving it in the positive direction along a number line. If you're moving it to the left, that would be the negative direction on the number line. So if we move this one twice, once and then twice, it's going to be the same idea as filling in the zeros over here. We only have to move it once to get it in front of the 6 and the 7, but we still have 1 more to go. So we have to fill in with a 0. So that's going to be 0.067. 0.067. Or if you want, you can do 0.067, either way. So that would be 67 1,000ths. If we were naming that number. Our next one says 5.88 times 10 to the negative fourth power. So we're moving it 4 spaces to the left. So if we move it once, that gets us past the 5. So we have to move it 3 more times. So that means there are 3 more zeros to the left of the 5, the 8, the 8. So 0.000 and then 588. And in terms of this number, that would be 10th, 100,000, 10,000, 100,000, millionth. So that would be 588 1/millionths. And then our last one, 3.8 times 10 to the negative first power. We're just going to move it once to the left because it's times 10 to the negative 1. So that would be 0.38. 38 100ths for that one there. So anytime you have a positive exponent, that number is getting larger. Anytime you have a negative exponent, this number is going to get smaller. Okay. Now, the reason why this is kind of mixed in with all of the exponent rules is because everything that you see with scientific notation contains exponents, and every single scientific notation number has the potential to be a like term with something else. So what we're going to be looking at is adding and subtracting scientific notation using our like term rules. Now, with like term rules, you not only have to have the same variable, right? I'm going to put variable in quotes because we don't have variables here, but we do have 10 and 10. And then we also have to have the same exponent. So we're looking for like terms here. And in order for them to be like terms, it has to be times 10 to the same exponent on both numbers, which works on number 13. It does not work on number 14 because we have 10 to the 7th here and 10 to the 6th here. So there are some adjustments that are going to be made here. And we're going to use something that is called, so it says make sure the exponents are the same, which is what I just mentioned. And so we are going to use LARS, which stands for left add, right subtract. This has to do with the decimal shift. If you move the decimal to the left, you add an exponent. If you move the decimal to the right, you subtract an exponent. That's what it's talking about. And that's going to be necessary on some of these in order to get the same exponent with our 10. Now, the first one, it's not going to make a difference. So here's kind of the cool thing with this is that 3.4 times 10 to the second plus 5.2 times 10 to the second is exactly the same. I'm just going to go over here for a second. That is exactly the same as if 10 were a variable. Let's say 10 was x. So this would be exactly the same as if we had 3.4 x squared plus 5.2 x squared. There is no difference at all in terms of this problem here and that problem there and how combining like terms works. So this one here, all you would do is add together the 3.4 and the 5.2, which is all we're going to do here as well. So remember that when you combine like terms, all you do is add the number up front or subtract the number up front, keep the variable, the 10, and the exponents, the 2, exactly the same. So if you add 3.4 and 5.2, you end up with 8.6. And so this equals 8.6 times 10 to the second power. Because this one over here would be 8.6 x squared. The only difference is that we have a 10 instead of an x. But because it's a 10 on both, and because the exponents are the same on both, that means they're like terms. All right. So that's it for number 13. Now, number 14 is going to be a little bit more challenging because the issue that we have on 14 is that our exponents are not the same. So we either need to change our first, our first scientific notation to get a 6 as an exponent, or we have to change our second scientific notation to get a 7 with an exponent. And it doesn't matter. It doesn't matter which one we do. It doesn't make a difference. So we could go with either one. I would suggest, because if you write, the answers have to be written in scientific notation. And scientific notation means you have to have a number that's at least 1, but also less than 10. I would recommend changing this second one to make it a 7. And so if you're going to add an exponent to this one here, that means we are going to, if we look back here, we're going to move the decimal to the left. So if we want to add on an exponent to make this a 7 to match this one, that means this decimal has to shift to the left once, because we said left add, right subtract. And if we move this one to the right, which we could do, that would make this a 6, but that would make this a 95. And 95 plus 1.1 is not a number between 1 and 10. But 9.5, and then we move this one to the left, plus 0.11, 9.5 plus 0.11 is still a number in between 1 and 10. So it makes it a little bit simpler to move the decimal on this one instead of this one. It just reduces one step at the end of the problem. So move the decimal to the left one here, which adds an exponent. So that basically adds an exponent onto that 6. And so we get 9.5 times 10 to the 7th power plus 0.11 times 10 to the 7th power. It's basically a balancing act. If you move the decimal one way, you have to compensate with the exponent at the end. And if you move the decimal the other way, you have to compensate oppositely with the exponent on the end. So it's essentially just a balancing act. And so we're going to add 9.5 and 0.11, which is 9.61. So the answer here is 9.61 times 10 to the 7th power. Because once we have our 10s with the same exponent, we can then just add the numbers in front of them. And that's all we're doing, combining like terms. For 15, any questions on those? Sorry, before I just plow ahead. Any questions on those before we move on? If not, we'll take a look at 15 and 16. So again, on 15, we've got a -4 with one of our 10s. We've got a -5 with the other. Again, it doesn't actually matter which of these you adjust. One of them might be a little bit easier in the end than the other in terms of which one you have to move. And on this one here, we want to basically get a -5 here or a -4 here. Now, if we got a -5 here, we would have to subtract an exponent from -4, which means that you would have to move the decimal to the right. And if you move this decimal to the right, that's 72. And 72 is definitely more than 10. So if we move the decimal on this one, we have to add 1 to the exponent to get to -4. That would move the decimal to the right, making that a 0.318. And this would be 7.24, which means if we added those together, we're still within between 1 and 10. Now, it's not wrong if you do it the other way by moving the decimal on this one. You just have to make an adjustment at the end of the problem. So let's move the decimal to the left on this one here. So if we move the decimal to the left there, that means we're going to add 1 to the exponent on the end there. So left add, right subtract. And that would be 7.24 times 10 to the -4th plus, or 0.318 times 10 to the -4th. So now we have the same exponent. And your calculators might come in handy here, 7.24 plus 0.318. And in the interest of time, I'll just go ahead and give you the answer. It is 7.558. The other thing about scientific notation is you're always going to use all of the values after the decimal place. If it's 5 numbers after the decimal place, write all 5 numbers. We're not going to be rounding anything here. And then that's going to be times 10 to the -4th power. All right, now this last one on our first page here, there's a lot of examples on the next page, which we're probably not going to do in terms of the adding and subtracting. So, all right, we'll do a couple subtraction ones, but we're not going to do everything on the second page. So this last one here, I'm going to show you what happens if you move a decimal and it doesn't end up giving your answer in scientific notation. So That would be if we were to move the decimal on our second one this time. So if we want to get from -2 to -3, that means we are going to be subtracting 1 from our exponent, which means that the decimal moves to the right. So if we move this one to the right once, that would give us 27, and we'd subtract 1 from -2, which would give us -3. If you were actually doing this one on an assignment or a test, I would recommend changing this first one, but I'm just going to show you what happens if you change the second one instead, because you still get to the right answer. So we got 6.8 times 10 to the -3rd power plus 27 times 10 to the -3rd power. And if we add those two numbers together, that gives us 33.8. So that equals 33.8 times 10 to the -3rd power. Which, as a number, there's nothing wrong with that, but this is not yet in scientific notation. Because this number is 33, which is greater than 10, so we still have one more decimal movement to make. And so we'd be moving this decimal once to the left. And if you move it to the left, here's our rule right here, left, you add onto the exponent. So -3 plus 1 would be -2. So we end up with 3.38 times 10 to the -2 power. And we could have gotten straight there if we would have adjusted our first scientific notation number instead of our second, but we can still get to that answer. It just takes one additional step at the end to convert back into scientific notation. So either way, we get to the right answer. One of the ways is a little bit quicker than the other, but you'll still be able to get there. All right, are there questions at this point about scientific notation, moving decimals, what we're doing before we move on to the next page? Because there's a little bit more with combining like terms, and then we're going to do some with multiplication. Okay, go ahead and flip the page. Also a little bit with division. So let's go ahead and skip a few here, and we will take a look at problem 22 and problem 24. So we'll just do those two, 22 and 24, and then we'll move on to some multiplying and dividing. So for 22, we got 4.2 times 10 to the -4th minus 6.8 times 10 to the -5th. And so again, we want to make sure that we get the same exponent before we add or subtract, because otherwise they're not going to be like terms. So we either want to subtract one exponent from the first one, or we want to add one exponent to the second one. And so we got to think about, all right, what are the rules here? So if we want to add one, that means we're moving the exponent to the left. So left add, right subtract. By the way, this rule here is going to be a big deal with what we're looking at today. So left add, right subtract, that is going to be very, very important. So if you circle that, just so you know where it is, or if you highlight it in some way, if you have a highlighter, highlighting that might be a really, really good idea. That way you can just go right back to it. If you forget what way to move the decimal and how to adjust that with your exponent, good thing to look at. So if we add one exponent to the -5, that would get us to -4, which would move this decimal to the left one, which is actually probably what we want to do. So +1, because when we do that, that gives us 4.2 times 10 to the -4th minus 0.68 now, times 10 to the -4th. Which is great because 4.2 minus 0.68 is still a number between 1 and 10, which means our answer is just automatically going to be in scientific notation. 4.2 minus 0.68 is 3.52. So that's 3.52 times 10 to the -4th power, keeping our variable, in quotes, our 10, and our exponent exactly the same because these were like terms up here. So give 24 a try. Try number 24 on your own. See if you can work that one out. I'll give you a minute or two on that, and then we will have a look at some multiplication and division examples, and then we'll call it good. I actually think in some ways the multiplication and division ones are a little bit easier. Okay, here we go. So I went ahead and moved the decimal in the second number again, because to get from 3 to 5, that would be adding to this exponent, which means we'd be moving the decimal 2 spaces to the left on this one instead of just 1. And if we move it 2 to the left, that's 0.027. And if that gets subtracted from 5.3, we're still looking at a number between 1 and 10. Now, if you decided to move the decimal 2 spaces to the right on this one, that's fine. You get 530. And 530 minus 2.7 would be 527.3, which then you just move it 2 more to the left to add on a couple more exponents. So either way, you should end up at the end with 5.273 times 10 to the 5th power. All right. Working on some notes. Any questions on 24? Any questions on 24 before we look at some multiplication and division examples to wrap things up today? Okay. If not, let's go ahead and move on. Now, these last ones, these are the ones where it's going to probably be the most useful to use a calculator. And like I said, I think that these ones are a little bit simpler than the combining like terms. So the multiplying and dividing, we got 3 steps here. The first one says to multiply and divide the numbers. Basically what that means is use the product rule, right? We had, if you have an example of something like, let's say 2 times, or not 2 times, let's say 2x to the 4th times 4x to the 5th. You multiply the regular numbers, 2 times 4, which is 8, and then you add the exponents, which is 4 plus 5, so that'd be 8x to the 9th power. The exact same rule applies here with multiplication. You're going to use the product rule. You're going to multiply the regular numbers together, the coefficients, and then you're going to use the product rule or the quotient rule to change the exponent, either adding the exponents for multiplication or subtracting the exponents for the division. So on number 25, you're going to multiply 2.8 times 1.9. 2.8 times 1.9 is 5.32. Which is a number between 1 and 10, so we're good there. And then times 10 to the what power? Somebody tell me. Using the power rule, what number would we get with our exponent? Or not the power rule, sorry, the product rule. Add the exponents. 7 plus 4. 11, exactly. So the answer is 5.32 times 10 to the 11th. That's it. Some of these you'll probably have to make some adjustments to at the end, because when you multiply or divide, you don't always end up with a number between 1 and 10. let's go ahead and try number 26. We're actually just going to do all of these. 26, 1.3 times 4.7 in the interest of time, that is 6.11. And then we're going to say times 10 to the what? 9 plus negative 5. Or 9 minus 5. Or sorry, 10, yeah, 9 minus 5 is 4, exactly. So 6.11 times 10 to the fourth power. So these first two problems use step 1 and step 2. Now step 3 is to use the left add, right subtract. To use the LARS. Use left add, right subtract to adjust the decimal and exponent in the final answer if needed. It wasn't needed on 25 or 26, but it will be needed on the next two. So 27, 3.4 times 10 to the negative second times 8.5 times 10 to the sixth power. All right, what's 3.4 times 8.5? Somebody plug that in real quick. 3.4 times 8.5. I see a lot of calculators. 3.4 times 8.5. $28.9. All right, so 28.9 times 10 to the what power? What's our exponent going to be? Was it? 4, yeah. Negative 2 plus 6, 4. Now, this is not yet in scientific notation because this first number is more than 10. So we have to move the decimal to the left. And our LARS says if you move it to the left, you add the exponent by however many you move the decimal place. So we move it 1 to the left. So we add 1 to the exponent. So that would be 2.89 times 10 to the fifth power. Move to the left 1, add 1 to the exponent. So that's it for 27. 28, same idea. 9.8 times 7.5, that is 73.5. Negative 24 plus 27 is 3. So that would be times 10 to the third power. 73.5 is more than 10, so we have to move our decimal once to the left. So that would be left, add to the exponent, so 7.35 times 10 to the fourth power. And that's our answer for number 28. So if the decimal gets moved, the exponent has to change. All right, we've got 4 more problems. These are all division. Now, whether the division is written as a fraction or not, you will still be using the quotient rule. So for the last 4 problems, you're going to be doing the exact same thing. You divide the regular numbers and you subtract the exponents. Now, it's a little more obvious with 31 and 32 because these ones are written like the ones that we've seen before. But it doesn't change the fact that this is still division on 29 and 30. So 29, you're going to take 3.72, divide by 1.2, and that is 3.1. And then subtract the exponents because we're using the quotient rule now instead of the product rule. 8 minus 5 is 3, so that would be times 10 to the third power. For number 30, 6.4 divided by 4 is 1.6, which means we're not going to have to make an adjustment on this one. And then subtract the exponents. Negative 4 minus 6 is negative 10, so that'd be times 10 to the negative 10th power. The last two, 31 and 32. And you'll notice that on these ones, we're never going to do just like simplifying fractions or anything like that. These ones start as decimals, they need to end as decimals. So even on 31 and 32, where they're written as fractions, because we have decimals and because scientific notation is written in a particular way, these will not remain fractions. That's kind of a big deal when you're dividing these. So 1.2 divided by 5 is 0.24. And -5 minus -6 is the same as -5 plus 6, which is 1. So that'd be times 10 to the first power. And this one's a little bit weird because, well, right now this number is not between 1 and 10, so we do have to adjust this one. We have to move the decimal to the right one. And when you move it to the right, you subtract from the exponent. So that would end up equaling 2.4 times 10 to the 0 power. And because we're writing our answer in scientific notation, this is how we would write this. 10 to the 0 power. What is 10 to the 0 power though? Based on what we learned last week or the week before. Yeah, it's 1, which means the answer here is just 2.4. Like this whole thing is just 2.4. But in scientific notation, we write it as 2.4 times 10 to the 0. All right, let's see. Last one, 2 divided by 3.2 is 0.625. And 6 minus -7 is actually 6 plus 7, which is 13. So it'd be times 10 to the 13th power. And we need to move our decimal in between the 6 and the 2. So that's to the right, and we're moving it once. So we are subtracting 1 from the exponent. So that would be 6.25 times 10 to the 12th power. And that's it. So that's our scientific notation lesson for today. We've got about 13 minutes to get started on our assignment, so we will definitely get that going.